Okay, physics friends, welcome back. We're going to talk some more about inclined planes, and today we're going to do an example. We're going to look at problem number 1. What if we have a box that's sliding down a frictionless incline? So here's our setup. We have a box. It's sliding down this frictionless incline at angle theta, and we're going to say that theta is 60 degrees. And you can see that I've already drawn my free body diagram, so I have the weight pointed straight down towards the center of the earth. I have the normal force pointed perpendicular to the surface. I don't have any friction because it's saying it's frictionless. And then I've drawn in my components for the weight. And then I'm curious to know what the acceleration the box experiences as it goes down this incline. Okay, so there are two ways that I could figure out acceleration. I could look at acceleration from a kinematic standpoint, or I could look at it from a net force standpoint. Now, if I think about kinematics, do I know time? No. Do I know the length of the incline? No. So right there, I probably won't be able to work with kinematics. So let's switch to force. And so when we're thinking about force, remember we need to think in the x and the y directions, where x is pointed down the incline and y is perpendicular to the incline. And if the box is sliding down the incline this way, well, then that means I'm going to be thinking about the x direction. So I'm going to want to think about F net in the x direction, or F net is equal to ma. And when I think about F net, I want to think about the total forces in the x direction. I want to think about the forces that are helping it move down the incline and the forces that are hindering its motion down the incline. So when I look at my free body diagram, remember helping forces are the ones that point in the direction of motion. And so as I look here, that tells me that Fgx is the helping force. So I'd write Fgx. And do I have any forces pointed up the incline? Because that would be a hindering force. And that answer is no. So it's just Fgx minus 0. You don't even have to write that, but just for fun. Fgx minus 0 equals the mass of the box times the acceleration. Okay. Now, how do I find Fgx again? Well, if theta is this small angle, that means this is theta here, and Fgx is the opposite side of the angle, so that would tell me I need to use sine. So I'm going to take the hypotenuse times sine of theta to give me Fgx. So this would be Fg times the sine of theta equals ma. And now to find Fg, or the force of gravity, or the weight, I need to take the mass of the box times the acceleration due to gravity of wherever we are. We happen to be on Earth. So Fg I can also write as mg sine theta is equal to ma. Now you might be thinking, wait, hold up, we don't have the mass. How are we supposed to solve this? Well, I like to tell my students if they don't give you the mass in the problem, that probably means you don't need it. And that you should just keep writing m until something magical happens. And what I mean by something magical is that, hey, if I want to solve for acceleration, I have to divide by m on both sides. And when I divide by m on both sides, m divided by m drops out. So I don't need the mass to solve this problem. And so I'm left with g times the sine of theta is equal to the acceleration, where g here on Earth, I'm just going to use 9.8, and the sine of 60 equals the acceleration. Make sure that you're in degrees in your calculator, not radians. And when you do that math, you get that the acceleration is equal to 8.5 meters per second squared. That's a really straightforward, basic inclined plane problem. We're going to do a few more, so hopefully I'll see you in the next video.